In our last section, we will take a look at solving exponential and logarithmic equations. At the end, we will consider some applications that result in an exponential or a logarithmic equation. We start by looking at some properties that will only help with some of the equations. We talked about the exponential property of equality. If the bases can be made the same, the exponents are equivalent. We will discuss those cases where the bases cannot be made the same in this section. The second property applies to logarithmic equations. If there are only two log terms, the same base, and if these are on opposite sides of the equation, the arguments can be set equal to one another. If these properties can be used, use them, since you arrive at the solution a lot quicker than the methods we're about to discuss in this section. To solve an exponential equation where the bases cannot be made the same, start by taking logs of both sides. You can use common or natural logs. If the base of one of the sides happens to be 10 or e, use a logarithm with that base, since this will help with simplifying. This exponential equation can be solved by the exponential property of equality, since 8 can be replaced by 2 cubed. This gives us a solution of 3. As for this exponential equation, we cannot make the bases the same, therefore we need to solve by taking logs of both sides. Since 7 and 25 are not 10 or e, it won't matter which base of logarithm you choose. The reason you are taking logs of both sides is now the power rule of logarithms applies. Log of 7 to the x is equivalent to x times the log of 7. The variable is null down and nearly isolated. Divide both sides by the log of 7. Approximate, go into your calculator. We are solving another exponential equation. This one has a base of 10. Therefore, when we take logs of both sides, we'll go with common logs. There is a rule that says if you can match the base of the logarithm with the base of what you're taking the log of, it simplifies to give you the exponent. So the left-hand side will simplify, giving you the exponent, and after you divide by -1, you are ready to take this to your calculator and approximate. We now move on to solving logarithmic equations. If the logarithmic property of equality can be applied, use this, since you'll arrive at your solution a lot quicker. If not, we start by combining any separate log terms into a single log term. The constant is moved to the opposite side, and once this is done, you are ready to rewrite in exponential form. Because you can only take the log of positive numbers, we must check by making sure that we are never taking the log of 0 or a negative number. Our potential solution needs to be placed into the variable of these arguments, checking for the sign. If the argument works out to be negative or 0, the solution must be eliminated. This log equation has only two log terms that are already on opposite sides of the equation. To solve, apply the logarithmic property of equality by setting the arguments equal to one another. This gives us a potential solution of 2. 2 is the solution if when we substitute it in for x, we are not taking the log of 0 or a negative number. When x is placed in the first term, we get 7, which is positive. Placed into the second log term, we get 3, which is also positive. Therefore, 2 is the solution to this equation. Before we rewrite in exponential form, we need to isolate the log term by subtracting 3 from both sides. The base of the natural log is e. Therefore, when we rewrite in the exponential form, we have e squared set equal to x plus 1. Subtracting 1 from both sides and then using the calculator to approximate for the potential solution. Remember, we need to check logarithmic equations. 6.39 put in for x would give us taking a log of about 7.39, which is positive. Therefore, this is our solution. This equation has more than one log term. Before we rewrite in exponential form, these two separate log terms need to be combined. Since the first log term is positive, its argument will go in the numerator. The second log term being negative, its argument will go down in the denominator. To write in exponential form, we write the base of 10 raised to the first power and then this is set equal to the argument. Since the argument is a quotient, I am going to write 10 over 1 so that I can go on to solve by cross-multiplying. Solving for x by cross-multiplying gives us a potential solution of 2. Make sure that if you substitute 2 back in for x, the argument remains positive, which it does, therefore 2 is the solution. We begin by combining the separate log terms into a single. Since both of the terms are positive, the arguments will be combined through multiplication. Next, we write in exponential form. 3 squared equals the argument x squared minus 8x. Since this is a quadratic equation, we set this equal to 0 and solve by factoring. We come up with 2 potential solutions, 9, -1. We're okay keeping the 9, but as you can see, with the check on -1, we would be taking the log of a negative number. Therefore, -1 must be eliminated. The formula we will be using is one for uninhibited growth. The formula a of t equal to a naught times e to the rt is what we'll use to solve these uninhibited exponential growth problems. A of t is the increasing bacteria population, a naught is the initial number of bacteria, r is the growth rate, t is the time. By the way, you may see this formula with other letters used for the variables. Don't let this confuse you. It will be the same formula. After the values are substituted in, we see that we need to be solving for an exponent. Before we take logs of both sides, divide by 100 to isolate the exponential factor. From there, we go on and take logs of both sides. The right-hand side simplifies to give you the exponent, since you have matched the logarithm to the base of what you're taking the log of. The last step is to divide by 0.037 and then estimate on the calculator. And we find that the bacteria will grow to 3,000 in about 30 years. Thank you for listening.